Okay, the last portion of this video on analytical solutions is seepage through an earth dam. So we just learned about how to do seepage through a rectangular section, and in this case we are going to take a simple trapezoidal cross-section of a dam. The assumption here that it's kx equal to ky, or it's a uniform soil, it's just one material, and with a single K. We're going to use the Dupuy assumptions. The top width of this is W. The height of water on the upstream side is H. We're going to assume it drains off the backside. I mentioned before that we often assume that the phreatic surface exits at the tailwater, which would be down here. In this case, we're going to assume it exits up here at this length, defined some distance up the backside, L, and that if you drew a vertical line through there, we'd have this CE cross section. And then just in general, here in the middle of the dam, we have this BF cross section up to this phreatic surface, and the slope of that line, the vertical axis in this case is Z, the horizontal is H, and it's a flipped axis, it's going back to the left, and so this is the slope of this line would be your the hydraulic gradient, which is one of the Dupuy assumptions. We've also, I think it's mentioned here, so we're gonna assume the Dupuy assumptions. I is constant along a vertical line. I, the hydraulic gradient, is equal to the slope of the free surface. Darcy's law is valid, and then curve A prime BC is a parabola. What does that mean? So this blue line down to here, and then all the way back, back to A prime, that's in the shape of a parabola. Okay, that's one of the assumptions we make. And then we're going to assume that this distance from the upstream toe of the dam back to this where the phreatic surface exit is delta, and because of that parabolic shape, that means that this distance from A to A prime is about 0.3 delta. So that's part of our discussion here. And then if you add up all these, another part of this is this distance. Based on this assumption as a parabola, this distance all the way back here is D. And we'll come back to that a little later. So first of all, we're going to look through the flow through section CE. So that is this section right here. And it's horizontal flow. So we're looking at the horizontal flow through section CE. And if we apply Q is equal to KIA, the hydraulic gradient is dz dx, which is the tangent of alpha. So right at this point, the slope is equal to the slope of the back of this dam, the slope of the phreatic surface, and so it's the hydraulic gradient is the tangent of alpha. That's one of our main assumptions here. And the area is CE times 1. So what that means is the cross-sectional area of flow is the height along this CE line times the 1 unit in the dimension perpendicular to the screen. So what is the height of that line? Well, using trigonometry, if you treat this as a triangle, L times the sine of alpha gives you this height right here. So we have L sine alpha. Therefore, the flow rate through this section CE is K times L tan alpha times the sine of alpha. So we've just plugged in this tan alpha and L sine alpha into this equation, and we get this equation for Q. All right, so that's equation 1. Remember that. And now we're going to look at flow through section BF. What is BF? BF is right here. and it's just somewhere here in the middle. And so now if we apply Darcy's law to section BF, the hydraulic gradient is dz dx, so it's just the slope of that phreatic surface at that point. The area, the cross-sectional area flow, the height of that line is z, and again, the other dimension is 1. So we have k times z times dz dx, and assuming continuity, the flow through section CE has to be equal to the flow through section BF. So if we set those two parts equal to each other, we get this equation. And then after we integrate that equation and solve for L, we get this equation right here. So it's, what have we got here? We've got D, we've got H squared. We've saved ourselves a ton of, we've skipped a ton of steps here in the derivation, but basically we've solved for this distance L using these, using this derivation. So that's equation 2. Well, this gives us everything we need. To solve for this, you have to compute alpha, delta, 0.3 delta, and D, because we have to plug D into this equation. Now remember, D is this whole distance right here, okay? And then we solve for L. Anyway, we compute alpha, delta, 0.3 delta, and D. We compute L from equation 2, and then we plug that into equation 1. So once we get L from equation 2, we go back to equation 1, plug in L, and we get Q. So there's not a simple equation representing the shape of the phreatic surface, but we do have an equation for Q. And, you know, calculating these geometries is the alpha, delta, 0.3 delta, and D. It's a little bit tricky, but once you set it up for, let's say you set up a spreadsheet that does all this geometry, you know, based on the height of the dam, the width at the top, and so forth, it's actually a solution that you can reuse. So you just plug in your slopes and your height and your width at the top, and you can immediately calculate Q. So again, if you want to get if you're dealing with a simple levee or a dam and you want to just quickly estimate, or some trapezoidal shape, you want to estimate the flow, this is a great way to do it. So here's an example problem. The slopes on the two sides don't have to match. They can, but they don't have to. If we had a levee that was 10 meters high, 3 meters wide at the top, 8 meters deep water on one side, 45 degree on one side, 30 on the other, you can compute the flow in cubic meters per day per meter of length in the opposite dimension. And this is an exercise we'll do in class, and then you'll have a solution that you can use for any problem going forward.